the afternoon session. It is a pleasure to introduce Andras Szenes from Geneva that will talk on intersection cohomology of Moduli spaces of semi-stable bundles on curves.
Thank you very much. Thank the organizers for inviting me. Thank you, Oscar, in particular. And yes, so this is joint work with Camilla and Olga. So it's joint with Camilla Felizetti and Olga Trapeznikova. And well, I'll explain slowly what it is. It's about intersection cohomology of moduli spaces of singular spaces. So I'll give some indications, but this is in certain sense a very classical right now subject, and as the example of the calculation is actually was first this project of calculating intersection cohomology of moduli spaces of semi-stable bundles was started by Francis Kerwin back in the early 80s, in fact, when just a few years after intersection cohomology was introduced by Goreski and McPherson. So just some notation setup. So I will not write the title, but it is intersection cohomology of moduli spaces of semi-stable bundles. Okay, so I will denote MDR is the moduli space. Okay, let's do it this way. Of semi-stable bundles of a degree D and rank R. So it's a question to the audience, but I decided I'm not going to define what this is in this. Should I? But anyway, so this is a moduli space of isomorphous, in first approximation, isomorphous classes of semi-stable bundles on a Riemann surface on a G Riemann surface or curve Riemann surface, which I'll denote by C, although this will not be used very much. So I'm actually not going to define what this is, but I'll do something better because I'll dissect it in absolute minute detail that even normally the experts don't do in a second. So I'll compensate with that. Okay, so we will actually be only interested when D is equal to 0 and 1. So the point is M0R is a singular variety, singular projective. Well, it's singular if G is greater than 2. And here probably G, well, let's assume it's greater or equal than 2 for now. It's a singular projective variety, while M1R is a smooth projective variety. And the dimension is, well, there's some little exceptions, but the dimension is equal to G minus 1 times R squared plus 1. Okay, so that's the, and so we will be discussing this pair of varieties. They are like brothers and sisters, and the sister is singular and the brother is smooth. And so this will play a very important role. So I'm an enumerative geometer, a algebraic topologist. So what we'll be interested in is describing, the cohomology rings, which encode the enumerative data, right? For example, for the smooth one, this was a very classical problem that were even before the time that I mentioned earlier. So this was at least the Betti numbers were calculated by Harder and Narasimhan, and and also Attila Bot, just a later motivated by their work. And since it's ever so slightly relevant, I can mention this anecdote about the calculation of the Betti numbers that I like very much, which is that the reason also you need to mention both of them, because Harder and Narasimhan did their work to as a test of the wave conjectures by calculating points over a finite field of this space. So this is actually just a test, assuming the wave conjecture. So it wasn't a theorem at the beginning. But then very quickly, the wave conjectures were proved, and then it became a theorem. While Attila and Bot used their famous paper on Young-Mills, the Young-Mills functional topology. In any case, they calculated at least the Betti numbers, and then the multiplicative structure. We also know a lot about it, in particular the work of Kirwan, verifying the Mumford conjectures, etc. So this ring is very well known. So our focus will be this M0R thing. Okay, so for M0R, we'll be interested in the intersection cohomology. So for the theme in general is that for cohomology, so we'll calculate this IH of M0R, at least the Betti numbers for now, but we can also calculate more general invariants. And so this is intersection cohomology. I'll give you an absolute minuscule introduction to it. This is a generalization of cohomology. Of course, you can also look at cohomology of this space, but they're usually not so great. I mean, one problem with them, for example, from the point of enumerative geometry, is that a usual cohomology of a singular variety doesn't satisfy Poincare duality. So you don't really have you can't intersect things in a certain sense, and that's why it's intersection cohomology. So the basic properties. One of them that I've already mentioned, that IH of X is equals to H of X if X is smooth. So this is a generalization. In the smooth case, this gives you the same thing. And I will not write in a very formal, detailed manner, but the thing that we recover, which is not true in general, that it satisfies Poincare duality and the pairing. So it also satisfies the fact that the top cohomology is one-dimensional for us, etc. So we do get some numbers, since enumerative quantities. So now it is, so IHX is a module over HX. So the cohomology still plays some role, and it is a module. The big thing that we lose, we pay some price for this, is that but no product. So no, a priori, no natural product on the intersection cohomology. And maybe this will be necessary, but also it kind of explains why this appears in algebraic geometry. It's because why it plays a big role, I'll explain a little more later, is in particular the sort of the Lefschetz package also holds. So to explain that, so it's the following ideas. We'll look at this, let's look in the degree of the class, so in IH. So this dot, of course, is a graded vector space, and you do the degree. So then here you have just the 0 degree, then 1, then oops. So it's 0, 1, 2, 3, and then you go well, if it's an algebraic variety, then it will go to, say, 2n, if n is the dimension of the algebraic variety. And so then the idea is the following. So here you have a 1, and then here, at least in the cohomology, you have let's assume X is projective. So it's a singular variety embedded in the projective space. Projective in this case, so then there is the omega, which is the degree 2 cohomology class, the class of the ample line bundle. And so then, because it's a module, I can multiply by that here. And so the Lefschetz package just tells you that if you are somewhere here in degree D and you start multiplying, then here, this is 2n minus D. So sorry, I don't know if it's visible. So it's 2n minus D here. So I multiply this by omega to the power, I think, n minus D or something like that. And this is an isomorphism. So this is this Lefschetz theorem. So this is still true. So these are the two big gains, and this is a little bit of a loss. So this and this is a gain, and this is a little bit of a loss. So that's the general trade-off. But this has lots and lots and lots of applications. And so studying it is a very natural problem. Okay, maybe I just give you one little example of calculation of intersection cohomologies, just give you an idea. And this is the following. Let's assume that Z is projective and L, I'm not supposed to write there. So LZ is some ample line bundle. So then you can form the cone of L by just taking the line bundle itself, and then the zero sections you contract to a point, right? So then you get a cone. Okay, so a picture is like this. I like red. So this is red is Z, and then this is the line bundle L, and then what you do is just you contract it like that. Okay, and that becomes a singular space. Now Z could be singular in this thing, but it could also be smooth. So if you want, let's think about it as smooth. So in this case, there's a very explicit formula, which is the following. So this is some proposition. So in this case, the cohomology, or the intersection cohomology of this cone is equal to, so it goes until, so I will use the same notation, this 2n notation for Z, so it also is dimension n. Then it's, it's dimension for some reason n minus 1 I chose, excuse me. And so it is a 0 for D less than n. Oh, sorry, no. Less than, more than, no, cannot be. Just a second. Just confused one. No, it should be bigger than n. It should be bigger than n, and it should be the primitive cohomology otherwise. So primitive cohomology of Z, L, you like, D in degree D. And so what is primitive cohomology? So the idea is that, you have, so what's happening is that this creates kind of these minimal vectors, right? And when we start in some D and then you start going up, there are these minimal ones, the primitive ones, which are not in the image of omega, actually. That's what's called primitive. And so it's exactly those that appear here. So there's a completely explicit way. So primitive. No. Yes. So, sorry. Yes, you're right. Thank you. Primitive, sorry, and primitive, not sort of in the image of omega, something like that. No. So this is always true. So that's why, so it's not written smooth, but I said you can think smooth, because if you think smooth, then this would be your first example of actually calculating intersection cohomology for a singular variety. But then you can actually, there's an iteration procedure that you can do to reduce it to a smooth case. But this statement is true for, and I didn't write smooth anyway, so this is true as. Okay, so this would be like an example of what it looks like. So it has to do with this Lefschetz theory somehow. Okay, so now I'll do something a little. So before actually writing down the result, I'll do a beautiful little exercise that I promised that is supposed to compensate for not defining this thing. And this is, let's say, I call this the parabolic. So this would be like, yeah, it's a space, something about intersection cohomology, and now the parabolic projection map. So this is sort of well known, but somehow I think some detail was missing in the, at least I used this in my thesis in 1991. What I'm going to describe for rank 2, but I missed some, I think, an important point. So I'll explain it now. Okay, so it looks like this. So the idea is the following. It's some sort of space I'll look at, say, M1, R, and there's M0, R. These are the brother and sister. And then the idea is that there is spaces up there. There's this P1R, the parabolic, maybe let's call it par, maybe, par, 1R, and this is par 0R. Two spaces. And so let me define them first. So these are the parabolic spaces. Usually parabolic spaces are defined using some weights, parabolic weights, and it takes a very long time to define it. So this is a real shortcut here. I mean, it's already a bit present yesterday. So it's the following. So here it looks like this. So this would be isomorphic classes of say, in this case, stable degree 1 bundles. So now it's the following. So I look at some bundle over the curve, and then, well, the degree is 1, degree equals 1. I don't know if it's going to work. A stable, which I didn't really define, but and then, well, the rank is R, so rank is R. Well, this is the obvious thing. And then, sorry, and then, sorry, so I didn't define the thing. Okay, and so it's a bundle, and the extra structure is an R minus 1. Sorry, yeah, a bit disorganized here. I apologize. So I fix a point in the curve, and so I look at an R minus 1 dimensional linear subspace inside VP. So this is the data of the bundle, and an R minus 1 dimensional linear subspace. We assume this thing about the bundle and nothing else, right? This is the definition, the real shortcut definition of the parabolic bundle. No weights, right? So in this, for those, so this assumes that you don't know what, it's much easier if you don't know what parabolic bundles are, because this is. Now in this particular, I can actually write down the weights. So for those who want the weights, the weights are these. This is P1R is equal to, so par 1R is equal to P, so the parabolic space with weights 1 plus R over 2R, 1 over 2R, like this. So they're all 1 over 2Rs afterwards. Like that, and so they're equal weights, and equal weights means that I kill, so these are the special parabolic spaces where you don't have a full flag, but just, so it's a variant of parabolic spaces, where you don't have a full flag, you just have a single subspace, okay? Oh, it's just because I want the sum to be 1. I make this, maybe it's not necessary. It's if you add a way to, you can just move them. But I do this because I have a convention, but that's from another piece of work, is that the sum of the weights should be equal to the degree. That's why. I want the sum to be 1, I normalize. Which is the same, but this is that. And this is, yeah. But it turns out that for this case, actually no extra stability condition appears, okay? And so that's it. So it's enough if the bundle is stable. And now the other one, I probably is not very nicely done. Need more space. Okay, so I have this point P. At this point P, I look at this. This R minus 1 means that this is an R dimensional vector space, and this is an R minus 1 dimensional subspace. Okay. So this is of course, this all the way up to isomorphism. And so then the par 0 thing is a little bit different. So there, if you want, the weights are different. So then it's like 1/2. Well, I won't write them down. But the point is the following, is that this is going to be a bundle V. Now I will have a line. So that's, instead of R minus 1, I have a F1 in V P. And all the same things, maybe, so the degree equals 0, rank equals R. And it's, I think I need to assume it's semi-stable, I'm not sure. But so the important thing is now I will say the following for every bundle. So this is similar to stability. For every subbundle W in V, we have either the degree of W is negative, okay, so then it's okay, or the degree of W is 0, that's permitted, but then the F1 is not in WP. Okay. So this is some very special situations for parabolic bundles, which I'm not defining. One is really nothing happened. I just fixed an extra thing here. And in the other case, it's the stability appears, the parabolic stability in this manner, that you choose a line, and then if the line, if the degree is 0, then the line cannot be in WP. Okay. So this is, turns out, so why these are, of course, so this is again, of course, up to isomorphism. Turns out that, well, there's an obvious map here. And it's pretty clear that this is actually a P1 fibration, a PR minus 1 fibration. Right? Because basically, well, you look at the universal bundle and you just choose a 4-dimensional one subspace in, and this is just a smooth fibration, and so that's what this is. And so here now we will this is this space, this here. So this is now a map to M0R. It turns out, so yes, it's M0R. And of course, it's not a fibration. Now, the beautiful statement, this is what I call the tautological parabolic Hecke correspondence, which says that actually these two spaces are canonically identical. Okay? So par 0 and par 1 are the same. So this is what somehow I think was a bit missed. I mean, usually you would just construct a map here, but actually there is a map here to the parabolic 0 space. Okay. So for us, what will be, from our point of view, what will be important, that we have a smooth, basically a very well understood smooth fibration here, which is the same as this, which then has a dominant map here. So this is some kind of general resolution. You have a map from a smooth variety to a singular one, and that's what will be important. Okay. So now okay. So now what I'll do is I'll actually define the rank 2 case. Not define, sorry, describe. So this is a R equals 2 case. And so it looks as follows. So I'll have a little table. So I didn't really explain, of course, how this is constructed, but now you will see it. So the semi-stable bundles are defined as they are defined, but then there is something that's called S-equivalence. So several families of semi-stable bundles could correspond to points. So let me describe that for you completely for rank 2. So I'll go like this. On my table, this will be the point in M0, 2. And then, yes, okay. How does it, did I do V? Okay. And so this looks like this. So V is stable. So in this case, if V is stable, then there is no problem. To each stable point, M02 corresponds a point. So this is fine. Now, it turns out that points in M02 can be, they are in bijection with something that's called polystable bundles, which just means direct sums of stable bundles. And in this case, it's very simple. I mean, either bundle is stable, or it's a sum of two line bundles. Then it can also be. Okay, so then we can say that V is equal to L1 plus L2, so if you like. And here I will assume that L1 is not the same as L2. Okay? So this is a polystable bundle. This is also a point in M02. But now with this S equivalence, there are many, of course, bundles that correspond to this, this point, because you can write down extensions of, so sorry, maybe this is not a good point. I'll just a minute. So this polystable bundle gives a point here, but there are many semi-stable bundles that correspond to this direct sum, and they're then collapsed by GIT. And so either you have this or you have this, and these extensions are enumerated by up to isomorphism by these, the usual P projectivization of the X groups, which turn out to be PG minus 2. So it's the G minus, this vector space is G minus 1 dimensional. And then you have another PG minus 2. So the final answer, if you want to know what are all the semi-stable bundles corresponding to this point, it will be PG minus 2. Then there'll be another PG minus 2 when you do the other direction of the extension. And plus then you have the direct sum. So just this point itself. Point, which actually is this bundle. This is the list of all semi-stable bundles over corresponding to this point, which collapse here. Okay, and so then the last case is when the two bundles are the same. So this point in M02, and in this case, there is it looks like this. You have a similar thing. So you have a P of the extensions like this, and this is just PG minus 1. Okay, and in addition, you have the direct sum plus a point. So the answer here, so here is just a point, here this, and here you'll have PG minus 1 plus a point. Okay. Okay, so this is, you have the list of all rank 2 semi-stable bundles on a curve. Okay, are there any questions about this table? Okay. So now the idea is the following, is that in fact what this map is going to do for us is going to resolve this. I mean, it's going to recover the information. When you do GIT, what's happening is that this big ugly fiber is collapsed to a single point. And this one is also collapsed to a single point. Okay? But when we look at this map, then these points will be sort of recovered. So that's the plan. Okay, so let's do this recovery. So I'll do that here maybe. So fibers of this map. And let me give this, this map a name. Let's call this pi. Pi. And so I will not go into great detail. I'll just give you a picture rather. So let's do a picture. So this is M02. And of course, M02 is singular. So there is two kind of points. So this is this point, this type of points, the blue ones, and then there is a red one. I like red. There are these red points. And these red points is only a finite well, sort of a finite set if you fix the determinant. So in the picture, I'll just mark them like this, finite set. So these are, the blue part is direct sum of two, it's a Kummer, and then the red points are the singular points. It's a Kummer if you fix a determinant, and these are the singular points of the Kummer, okay? And so now I'm gonna do the picture of that space. So again, generically, if I, over the white part, so this is the whole thing is the white part, this is the white point, this is a point, a stable point, the same thing happens, then you just choose a line in a two-dimensional space. So this is just going to be a P1, right? Then if you go here, then what you need to do is you will choose, so this is a PG minus 2, but in this bundle with this extension, you will choose a line. You'll choose a line, but this line cannot be L1 because this, if it's L1, then it will contradict this condition. So if you look over, this part, over this PG minus 2, you will, anyway, so we choose a line, so it will be a line bundle over PG minus 2. And then again, another line bundle over PG minus 2. And then there's an extra point corresponding to this point. So the net result is that you'll get something like this, blue. So here, it will be, so this should be much smaller, I'm sorry. This is a small, it's P1. And now this is a much bigger one. This is PG minus 2, PG minus 1. These are two copies of PG minus 1 joined at one point here, okay? So a bundle of PG minus 2 on the left-hand side, and a bundle of PG minus 2, and the point joining them. And then finally, the last one, if you take a point, and then over that point, you will just have a PG minus 1. Okay, and then you have a PG minus 1 because the point is, it cannot be stabilized by a parabolic structure, and you just have PG minus 1. Okay, so this is your picture. Okay, so if you don't take anything away from this talk, there's just this. I think this is a a gorgeous thing. And of course, all together, when you take the union of this is the smooth space, this par 0, which is equal to par 1. So when you take the union of all these fibers up there, it's a smooth space. Okay, and this is. Yeah. So that's funny. It's what happens the following is that because of this, you see, it's all up to isomorphism. So it turns out that up to isomorphism, when you do an extension, because there is this extra group, this Borel, that it kills the movement of the line. So it's just a single, to each extension, just a single point corresponds. On the other hand, if you take the direct sum, it cannot be stabilized because every subline is actually a line which is similar to, which is an L, a copy of L, and it will contradict this thing. So this point does not appear. It's not stable. It cannot be stable. So the point is that you can stabilize those bundles and separate them, but this cannot be stabilized. Yeah. So I think it's a very nice exercise in if you want to understand bundles and curves, this is like a great exercise to understand this. But for us, what will be important is that you have this smooth space now. This is this P0 mapping onto M0. And we understand the fibers of this space, and I'll explain why that's important. Okay. So Now, maybe just very quickly, I'll explain the result. So the result is I don't want to spend too much time on this. So the theorem, that's one of the results. I mean, that comes out, the enumerative, so the Betti number result that's analogous to the Harder-Narasimhan and Atiebot statement is something like this. So this is our, so this is like this, 1 plus sum of r minus t to the power r squared 1 minus g. And then p minus t m1 r times p minus t p r minus 1 times q to the r. So if you look at this, this is simply the generating function of all the, these are Poincare polynomials of those Harder-Narasimhan Betti numbers. And you write down, you multiply them by PR minus 1, and you write down a double generating function, which now depends on T and Q. But this is just a generating function. It gives you all, this is the Poincare polynomial. Okay? And so the claim is that this is equal to what's called a plethistic exponential of the same thing. T square G. Okay. Something that's called the plethistic exponential. So here you just have the generating function of all the M1s, the brother, and then you have here the generating function of all the intersection Betti numbers of the sister with some shifts and some stuff. Okay, and the plethistic exponential is basically just an exponential. It takes addition to multiplication in the following way, that if you have a sum of ak t to the AKR, sorry, t to the k, q to the r, you take a polynomial, say, like this, then the plethistic exponential will take it to the polynomial ring. And then, so it's the product of 1 minus t to the k and q to the r. And maybe, I think it's minus ak. Something like this. So it takes addition to multiplication, creates a generating function, that's what it is. The way to look at this is that this is sort of the Hilbert function of a polynomial ring whose generators are here, right? Because when you take 1 over 1 minus something, it just gives you the polynomial ring. This is, you can think of it that way. Okay, so just to give you a quick example, you take, so let's do r equals 2. So then what that means is that you look at the coefficients of q squared on both sides and you compare them. So then you get the following equality, e minus t m1 2 cross p1. Okay, it's not really a product, but the cohomology is the same. And then plus t squared, t to the g minus 1, sorry. IP plus minus M0 1. So this is a Jacobian M0 1. Okay. And so this last second term is just 1 minus t to the 4g 1/2. So this part. This part, I write it down explicitly, plus minus 1 to the g minus 1. Sorry, don't need g minus 1 times 1/2 times 1 minus t squared to the power 2g. Yeah. Oh, so, thank you. Yes, of course. Yeah, I forgot. Sorry. I had an error in my notes. Say it again. Here, it's a minus. Yes. I think. Yes, yes, because if it's E, yeah, okay. Sorry, I just missed the R. Okay, so I just want to point out one thing here. So yeah, though this would take some time to understand, but why this is so. But so the main point is, as I said, it looks like there's this important sign that we're just discussing. So if the A is positive, so then if the coefficient is positive, then it is an even polynomial ring. If it's negative, it's an odd polynomial ring. And that changes things. And so amusingly, exactly in this case, something very special happens. If the rank is 2, and then there is this strange factor, a sign, depending on the genus. Okay? And so why is that? So and what does this even mean? So this plus minus I didn't really explain, but it just comes out of this. But the point is the following, is that this sign, it comes because the way to think about it is that you shift up so you write down sort of the Poincare polynomial. You shift it up by this factor, which is if G is even and R is 1, this is the second term correspond to the two factors of R is 1, and this is an odd, there's a minus sign which appears here, and it shifts up all the cohomologies of the otherwise very simple spaces, just product of two Jacobians, but it shifts it up by an odd number, and they become odd polynomial generators. And the square of an odd polynomial generator is, for example, 0. And in particular, you can see, just show me one thing, is that if G is even, then this 1 cancels here. And that 1, it comes from shifting up here the constant element of M0, the one cohomology class, and it becomes odd, and its square becomes 0. So this is a little clever, and that's why it's not so easy to decipher, and it wasn't so easy to find this formula. That was, by the way, found by Kerwin and collaborators a long time ago. No, it's a formula. A formula that I'm explaining now can be, sorry, I missed something. No, I made a mistake. Yes, sorry. I didn't make a, just a second. Sorry, yeah, I made a mistake, sorry. No, you're right, yeah, there's a mistake. Sorry, sorry, you're completely right, yeah. I copied the thing wrong. I got very excited about this. Sorry, no, sorry, so yeah, I apologize, yeah. So sorry, so this was the left-hand side of this thing here. I look at the Q square term, and then I look for a Q square term on the right-hand side. And the Q square term can come either from just M02, and that's this one, or it can come from, because it's an exponential, there's a product in it, from the twice the Q1 term, the rank 1 term. And I jumped ahead, and I was focusing on this other term, this rank 1 term. Okay. So this corresponds to here the two rank 1 things, and here this corresponds to the rank 2 thing. In this formula. So you see here, this is the left-hand side for the Q square coefficient of the left-hand side. This is the left-hand side. And then this is the this sum is the Q square coefficient of the right-hand side. Q square coefficient of the right-hand side. This is the right-hand side. Okay. Sorry. Okay. So where am I? I have 10 minutes left. Okay. Well, I have to really, now I want to explain how it works. So what should I use to erase things? I guess the idea was that one shouldn't write more than one. Okay. Let's start here. So my last topic is the method. And the method is this amazing generalization of, it's called the decomposition theorem. So this is the decomposition theorem. And I won't tell you all the history, but it is a far-reaching generalization of the Leray-Hirsch theorem. So realization of the Leray-Hirsch theorem. Now, yeah, I'm a little short on time, so I will not tell you what the Leray-Hirsch theorem if you don't remember it. So if you do, this helps. Let's say the theorem has the following form. So if you have a smooth, it's a map from a smooth, let's say everything is projective, to a possibly singular space, X, a proper map, you write X as a stratification of, which is corresponds to this map. Let's call this pi. And now then you can do the following thing. You can look at P. So this is my version of the decomposition theorem, which is much simpler than the general one. So you look at an open neighborhood, and you look at one of the strata. So then you can define LP, which is just a vector space, which is defined as the kernel of the map, of the restriction map from pi inverse U. So this U is, again, is an open neighborhood. U minus xj. Okay, so you just look at the restriction map locally at this point, and so of the complement of the stratum, and you call that LP. So this LP is sort of a quotient of the cohomology of the fibers that I was calculating of this P. Okay, so now for each of these things, what I will do is I'll take the corresponding cohomology, which is in this case, it's easy to calculate. And then in each cohomology group, I'll find a kernel. I will look at this at local, a neighborhood like this. I look at the restriction. I will look at the kernel of the restriction. I get a vector space LP, okay? All right. So now this defines a local system on xj. So just put together these fibers. It will be a local system. And so then the following thing is true. So I'll have to abbreviate this a little bit, unfortunately. So I can decompose, that's why it's called decomposition theorem, the total cohomology of X as a direct sum over all these strata of basically intersection cohomology of xj but with values in this local system. Local system, sorry. I want a notation for it. Lj on xj with values in this local system. So it's if it's constant, then it is just the intersection cohomology we're discussing. If not, you need to just, there is a certain algebraic twist in it. And the claim is that this theorem, our formula, is just precisely the decomposition theorem applied to this map. Okay? In particular, for example, here, why you have these products here? Because this is by the Leray-Hirsch theorem, by the way. We claim that the cohomology of this P par 1, which is the same as the par 0, is the product of the cohomology of M1. So in particular, with PR minus 1, so in particular, you can say that this thing here, it just, oh, now you won't see it, is just the P minus T of R, say 0. Okay? Or it's the same as par 1 because of the Leray-Hirsch theorem. Okay, so our plan, what this equality that I'm writing here, so this is exactly this par, this x tilde, this par 1 or par 0, which is the same. And then we write its cohomology as the cohomology of this product. Like I wrote it here, this is where it appears. And then this direct sum on the right-hand side, there is this direct sum, which then I'll have to explain this plasticity exponential, blah, 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 which, as you can guess, I'm not going to completely explain, but I'll do some justice to it. Are there any questions now? So the only thing I wanted to point out that so the decomposition theorem decomposes the cohomology of the total space, which in our case is this par thing, and it decomposes it into these spaces, and then I'll use some induction to kind of, but I'll recover exactly that form. Okay. All right, and so the last thing would be maybe just a quick what it looks like, the work itself. So I'll do it for rank 2. I mean, very roughly. Well, it's this plasticity expansion. I mean, what you can see is happening if you multiply this out. But already here you can see it, that the rank 2 odd space, the par 1, there will be some pieces on that decomposition which lie. Actually, maybe we can even do this now. So what does this look like for this case? We can already discuss it. Here's this map. You can see the stratification. This is the stratification. These are the xj's, right? The white is x0, the blue is x1, x2, or the red is x2. To each of these, I will have a direct summand of the cohomology. That's what it says here, there, right? And the white one will just contribute this thing here, because the generic fiber is P1. The blue one will contribute, actually that's what I wanted to do, but anyway, this factor. And then the red one, it turns out it doesn't contribute. And so maybe I'll just explain, I have still 3 minutes, exactly what you get, how this works out, okay? But it's exactly that, what I wanted to explain, how this works out. So it works out as follows. So I have my picture here. It's a bit far from this thing. So again, so what do I need to do? I need to decompose some, so I need to decompose the cohomology. So this is the global version, or maybe I cannot avoid it, I wanted to, but I kind of need to do the local. So this is the global, and this is the local version. And the local version looks like this. So that instead of, by local, I mean, I don't take the cohomology of the whole thing, but it gives me an equality about the fiber itself for each point. Okay, so that's what I call local. But it's still usual cohomology, not intersection. It's a bit confusing. Is equal to the direct sum over, again, over all these j's of the, so now this is going to be some what's called intermediate extension sheaves, but it's basically also just some intersection cohomologies. So I cannot give it complete justice. At the point P. So it's more or less some local intersection cohomology at that point P, okay? Which we will now calculate. So you'll see then how it works out. Okay, and so the idea then is the following. This part, so this term, the white term, so this just comes from the idea that so again, I'm looking at this thing, is that I have this xj, I have the local, so the local system, it's a bit confusing. It's only defined, as you can see, on the stratum itself, but then the intersection cohomology is interpreted as is defined on the closure. That's what it's a little bit confusing. But in any case, so here, this Lj is just, this map is trivial, and so we just have, this Lj is just equal to the cohomology of P1 of the fiber. Okay, so its Poincare polynomial is equal to 1 plus t squared. And did I forget about it? Oh yeah, well here you just have this, yeah. So here's just extra factors of P1 that I put in there. So that's there. Okay, so the most interesting part is the second part. Okay, this is the second part. And so here, well, I'll just have time to write down the equation. So what is happening is okay, so I'll just take one more minute, okay? So what it looks like. So the idea is the following. So I need to calculate the intersection cohomology, the local intersection cohomology at these blue points in kind of in this transversal direction. That will tell me the intersection cohomology of what this thing contributes to the cohomology of P. So what you get is basically a decomposition, maybe I'll just say it this way. You'll get a decomposition now, not of the whole cohomology, but the cohomology of each fiber separately. That's the idea. And so let's just look at what they look like. So this is a very simple case. You can see what the cohomology here is. It's just the cohomology of the fiber here is just a ring with two generators and then quotiented by the ideal x1 to the g, right? X2 to the g, that's and then x1, x2, right? So this is two P1s glued together with along a point. And so you take this thing, and now you have to calculate sort of this map if you'd like to. And so what turns out is you need to subtract from this, and so this calculation I don't have time to explain, but you need to this ideal that you have there that you need to subtract is an ideal that looks like something like so it's the cohomology of P1 times something like U y to the g minus 1. And anyway, yeah, I don't have time to explain this. The important thing that I wanted to point out that what I can tell you finally what the result is. So the final result, LP in this second case is just equal to it's a one-dimensional subspace is one-dimensional. And so here we are, you see x1, x2, and it's inside in x1 in x1 to the g minus 1, x2 to the g minus 1. Okay, so there's a two-dimensional subspace in this ideal, which is this one, and in that two-dimensional subspace, it's a line whose sign depends on g. Stop here.
Any question for Andras? Microphone? Is there any microphone around there? Yeah.
Yeah, you said both in the beginning about this intersection cohomology not being a ring, and then in the plastic exponential again that I should think of it as being a symmetric algebras.
Yes, that's
so is there a way to interpret this as such that this exponential really gives me an algebra isomorphism, that this intersection cohomology of the pieces recovers the algebra structure that you see on the other side?
So this is sort of, I don't think this has been done completely by but again, which algebra do you mean? Because you have to be careful, right? So the point is that these algebra, you're right. So the interpretation is that it's just the Hilbert polynomial with a double graded algebra, right? Whose generators have these weights. But those things go across different Q's and R's. So they actually, so if that's what you're asking, well, now I thought about it. So this would link different intersection cohomology for different different rank spaces. And to some extent, we have that, but this is subtle, yeah. That's because the decomposition theorem is is a complicated thing. But there is something like that, yes. But I would not want to, I cannot formulate a theorem. So I just need to make one quick comment because I forgot the attributions at the very beginning, which is that, so there is this work of, so there's some work by Reinecke, Mozgavo, and Meinhardt, whose work we used and who derive a similar formula in a different setup. So there's some preceding work to what we've done.
Good.
You expect some motivic refinement of this statement? I mean, is this equality?
So we can do, for example, this setup. We can do Hodge numbers also. So we can get some motivic information. After all, then I'm actually I cannot say any more right now, but the one point is that I'm not a big expert, obviously, on the decomposition theorem. It's like a pedestrian, like this decomposition I wrote down is a pedestrian approach. If you look at like Williamson or something, it looks nothing like that. For example, I didn't mention perverse sheaves. I don't know if you noticed. I think it's a nice invention not to do that. So I can actually do this whole thing without perverse sheaves. But yeah, so the whole point of this is that I think I brought down this subject, or we brought down this subject to more classical moduli theory.
I have a delicate question. Why did you choose the sister to be the singular one?
I know you were going to ask that. At the beginning, I was saying brother, sister. I said that because B in the alphabet comes before S, okay? And then when I write the formula, on the left-hand side, you have M1, and on the right-hand side, you have M0. So I start with B, brother, and then S, sister. That was the second one. But in fact, thank you for mentioning this. From now on, I will actually vary, next lecture I give about this, is the other one's going to be the sisters. So there won't be any discrimination whatsoever.
Fair enough. So we have coffee now before Nigel's Ramanujan lectures, but let's thank Andras again.